Hey everyone, and welcome back to the channel. In today's video, we're diving into a fascinating simulation project where we'll analyze the release of heat and combustion gases from a single car with an engine fire inside a ventilated parking garage. This is modeled as a steady-state analysis, meaning we're assuming the fire has already reached a stable, fully developed stage. We'll walk you through the setup, simulation process, and interpretation of the results. Perfect for those working in fire safety engineering, CFD analysis, or anyone curious about real-world simulation scenarios. If you find this content helpful, don't forget to hit the like button and subscribe to the channel for more simulation tutorials and engineering insights. The overall concept, let's take a closer look at the boundary conditions used in this simulation. These conditions define how the fire behaves and interacts with the environment inside the parking garage. Gas mixture, we're dealing with a mixture of nitrogen, oxygen, carbon dioxide, and water vapor. This represents the typical composition of air along with combustion products. Exhaust velocity. 6 meters per second. This is the velocity of the hot gases exiting from the fire source. It reflects the energy and pressure of the fire gases being expelled into the garage. Momentum source, 80 newtons per cubic meter. This represents the force per unit volume acting in the jet regions, simulating how the fire plume pushes and moves surrounding air due to combustion thrust. Flue gas flow rate, 0.1 kilograms per second at 1,200 K. This is the mass flow rate of the hot gases being emitted from the engine fire. The temperature of 1200 Kelvin simulates a fully developed fire scenario. Turbulence model, K epsilon, we're using the K epsilon model, which is one of the most common turbulence models in CFD. It helps us accurately predict how air and smoke mix and flow turbulently in the garage. Radiation model, discrete ordinates, DO, with WSGGM for the radiation heat transfer, we apply the DO model, which calculates radiative energy exchange between surfaces and gases. The weighted sum of gray gases model, WSGGM, is used to approximate gas absorption behavior, especially important for high-temperature gases. Inlet temperature, 300 K. This sets the initial ambient temperature of the garage, which is about 27 degrees Celsius, representing normal environmental conditions before the fire develops. These conditions give us a realistic and detailed simulation environment to study the spread of heat and smoke, and how ventilation affects fire dynamics. Alright. Now let's talk about what you'll actually learn in this workshop. This session is packed with practical, hands-on skills you can apply to real-world simulations involving fire, combustion, and buoyancy-driven flows. Here's what we'll cover: how to set up a CFD case with multiple species, like nitrogen, oxygen, to realistically simulate fire and combustion gases. How to define absorption coefficients for flue gases using radiation models, a critical step when dealing with high-temperature environments and radiative heat transfer. How to activate gravity and set up operating conditions to properly capture buoyancy effects, which are essential when modeling hot gases rising due to fire. How to define volumetric sources like heat or momentum directly in the domain, for example, simulating the heat released from a burning engine. How to use calculation activities to dynamically change solver settings and even boundary conditions during the simulation. This gives you advanced control over how the case evolves. How to monitor the solution and judge convergence using residuals and surface monitors, ensuring your results are reliable. And finally, how to post-process a case with multiple species, visualize temperature, gas concentration, and airflow to understand how the fire spreads and how ventilation impacts safety. If you're ready to boost your CFD skills and tackle challenging fire simulation problems, you're in the right place. The setup, make sure you have all the required files ready. I've provided the prepared files you'll need for this workshop in the video description below, so feel free to download them and follow along step by step. Here's what's included: garage.msh, this is the mesh file of the parking garage used in our analysis. calc_activities.ju, a journal file that automates some steps during the calculation. Multi-species solved. WBPZ, a Workbench project file with the simulation already solved, in case you want to directly explore the results. Just download the files from the description, place them in your working directory, and you'll be ready to begin the simulation with me. Alright. Now let's move on to the software and begin building our simulation. To get started, we need to open ANSYS Workbench. You can do this by following the path. Start Programs ANSYS 13.0 ANSYS Workbench. Once Workbench is open, we'll set up our project. First, drag a Fluent component system into the project schematic. This system will handle all the CFD settings and solvers we need. Next, let's rename the system to Garage. Just right-click on cell A1 and select Rename, then type Garage. Now we're ready to begin configuring our case step by step. Alright, now that we have our Fluent system set up, let's manage the external files required for this project. First, when you save your Workbench project, it automatically creates a folder called User Files inside your project directory. This folder is where all external files related to the project will be stored and synchronized. So, from the Workbench project page, go ahead and save your project to your working directory with the name Multispecies. Once saved, open your project folder. You'll see the user_files directory inside. Now, simply copy the two files, garage.msh and calc_activities.ju, into this user_files folder. This way, ANSYS Workbench can easily link these external files to your project. If you want to check which files are linked, go to the Workbench View menu and check the Files option. You'll see a list of all associated files right there. This keeps everything organized and ready for the next steps of your simulation.